In this last application of the derivative, before we get into integrals in the next chapter, let's talk about related rates, which is a little bit unusual because we usually take the derivative as a function of x or whatever the variable is, and that's why we use the prime notation. So, for example, f prime of x represents the derivative with respect to x. But what if we have all quantities and or variables that are functions of time, which is usually everything changes with respect to time. So if we have the explicit expression, which means an actual expression, let's say 2 plus 5t, then we know how to take the derivative. Once in a while we use the chain rule, especially if it's within another function. But what if we want to use the chain rule implicitly, which means without knowing the actual expression? How do we do something like that? Let's scroll down. For example, when we try to take the derivative of 5x squared, so this is a function, so we do not see any t variable, but we do know it changes with respect to time. So a lot of times we don't know how it changes. For example, if we did know, let's say x equals 1 plus 2t, so x itself is a function of t. If we do know the function, then we can use chain rule. We can plug in, and if you recall how to use chain rule, we multiply 5 by 2, so it becomes 1 plus 2t to the 1 power times the derivative of the inside expression, which is just 2, so it becomes 20 times 1 plus 2t. Okay? But what if we don't know? Then we have to use an implicit differentiation. What does that mean? It means we pretend sort of that the x is a function of t or whatever the variable is. Here is the different notation that we're going to be using. For example, dx dt represents change of x with respect to time. dy over dt, that's the change of y with respect to time, or the revenue or area or anything you want. This is how we can use the notation. So when we want to differentiate 5x squared, but with respect to t as opposed to x, then we have to use chain rule, but we're assuming x is a function of t or sort of the outside function. So how we would do this is we take the derivative of the outside first, which is 10x, times the derivative of inside function or x with respect to t. So that would be dx dt. And that's why it looks like that we're attaching this differential at the very end. Okay? And let's see how this works with an equation before we attempt application. Let's say if both x and y are functions of t, and we want to find dy dt once we take the derivative, and we're actually given dx dt, x, and y. So we have 8y cubed plus x squared equals to 1. So first we gotta take derivative of both sides implicitly, okay? So 8y cubed, the outside is 24y squared, but then times the derivative of y with respect to t, that's dy dt, plus, let's do the same thing with the x, that's 2x, but times dx dt. So again, we use the chain rule. Equals to, now with constants, we treat them just the same as always. The derivative is 0, okay? And now we can plug in all the variables. So it's 24, we recall y was negative 1, times dy dt is unknown, so we keep that, plus 2 times 3 for the x, and negative 2, I believe, let's see, dx dt, I think it should have been positive 2, excuse me, if you put that little positive, okay? Yeah, is that correct? 2 times x times y, yeah. And so then we can solve for it. All right, I think the sign is incorrect. Maybe this should be plus. Yes, because I think it was just a minor typo. dx dt should be positive 2. Okay, so we get negative 24 dy dt plus 12 equals to 0, which means this should be a little minus right here. Okay, so, and then we divide, I think we should get the positive a half. So double check your signs when you're working on these, but it's basically plugging it in, whatever you're given, okay? Same thing we can do in the next example, except notice how it's 2x times y. We're actually going to be using product rule in addition to the chain rule. So let's attempt that. First, I'm explaining how to take the derivative of 2xy. Well, notice first we're going to be differentiating x. So you'll get 2. Whenever it's x to the 1 power, the derivative is just 1, but then you multiply it by the derivative of the inside. So that's dx dt. So sometimes we just say if it's just a variable, the derivative is, let's say, dx dt in this case. Or derivative of a is dA dt, or cost is dc dt. We'll see that again. Times, we keep the y, and then plus 2, you keep the x, but then you differentiate with the y, so you get dy dt. Okay, so the full derivative, so this is the derivative of 2xy. So 2, differentiate the x, you keep the y, plus 2x, and then you differentiate the y, minus 5, I think it was 5x if you recall, yes, so derivative would be 5 dx dt, and plus, I think the y was 3y squared, so we're actually going to get 6y dy dt. And that's equal to 0 because the derivative constant is 0. And then we plug in all the values that were given. So dx dt was given, the y was given, the x was given, but the dy dt was not. So this is like a little algebra here. So we have a couple of terms with dy dt. So if you combine them, we'll get negative 6 dy dt, but then you get 54, you move it to the other side, and you can solve for it. And I think you get positive 9. And let's see how this works with applications. So typically you're going to have a couple of rates. One of them is known and the other one depends on the first rate, and we can find it. For example, let's check it out with the business application, revenue, cost, profit. Given the revenue and cost functions, and here they are given in dollars where X is the daily production and sales, find the following when 40 units are produced daily and the rate of change of production is 10 units per day. So you're given the quantity, 40 units, and the rate of change is also given. So it's important to translate what you're given first, which we're going to do. But in A, we're supposed to find the rate of change of revenue with respect to time. Okay. So we're actually given x equals 40. Let me write them out actually. So we're given x equals 40, and we're also given the change of x, which is dx dt, rate of change. So this is the change of production equals to 10. Okay, so it's important to write down what you have already. And now we are differentiating the revenue equation. So we're going to focus on r equals to 50x minus 0.4x squared. And you want to differentiate it with respect to time. So how we do it, the notation matters here a lot. So instead of writing r prime like we usually would, you would write dr over dt. So this is derivative of revenue with respect to time. And remember, when it's just a variable to 1 power, that's the derivative, equals to 50, recall the derivative of x, that becomes 1, but you get dx dt, minus, and then you differentiate the outside, 0.4 times 2, that's 0.8. You keep the x, because it just becomes x, so this is the outside, times dx dt, the derivative of the inside. So again, it's always chain rule. So this is the notation we use, and then we plug in. Notice this is what I wrote in the beginning. X equals 40, dx dt is equal to 10. So you can plug in everything and you get the answer. It's actually $180, and I think it was per day. So I wrote it whatever the unit of time is. So revenue looks like it's increasing by $180 per day. Okay, this is the interpretation. The rate of change of cost with respect to time can be done very similarly. I think the cost was, let's recall what was the cost equation. It was 5x plus 15. So if we take the derivative, we get dc dt, this is the notation of derivative of cost with respect to time, equals to 5. Derivative of x was dx dt, and the 15 was gone because it was a constant. So notice here we only plug in for dx dt because we have no x. So we get 50. So the cost is also increasing, but it's a little bit less than revenue, so this is good. So it's $50 per day. The cost is also increasing. And the profit, rate of change of profit, you actually don't have to find the profit equation and recalculate it. What we can do, what we remember from derivatives, is dp over dt, or rate of change of profit with respect to time, equals to dr dt minus dc dt. Remember how you can subtract the derivatives. So the derivative of revenue minus derivative of cost. So you can actually subtract your results, and that's $130 per day. So that's sort of common sense. And so it's increasing at $130 per day. All right, so let's take a quick look at a couple more applications, like the area. So let's say a rock is thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle formed by a ripple increases at a rate of 2 feet per minute. Find the rate at which the area is changing at the instant when the radius is 4 feet. So this has to do with the area of a circle, which we'll see in a few applications. It's A equals pi r squared. And again, when you're given all this information, it's important to translate it. For example, typically we're either given dr over dt, how the radius is changing, which we are given in this case, or how the area is changing. But what we're trying to find is how the area is changing. dA over dt equals to when r equals to 4 and dr over dt equals to 2, because that was the rate of change. 2 feet per minute, actually. So area of a circle is pi r squared. So keep in mind this equation, because we'll be using it again in chapter 7. And then we just simply take derivative of this equation. Derivative of A is dA over dt equals to, pi is a constant, so we keep the pi, derivative of r squared, that's 2r times dr dt. That's the derivative of r with respect to time. Okay, and now we can plug in everything. That's 2 times 4 times 2, so we'll get 16 pi, which you can keep that as the answer, or multiply by pi on your calculator, and you get about 50.27. And the units are feet squared per minute. This is the area, and it's changing per minute. And that's it. There's a very similar volume example, which we'll see volume of a cube quite a bit also. That may be on your exams too. So you have an ice cube that is 3 centimeters on each side. So this is like a square cube essentially. And it's melting at a rate of 2 centimeters cubed per minute. How fast is the length of the side decreasing? So volume of a cube is length times width times height. And if they're all the same, then they're all three are x. Let's say we call it x. So that means v equals x cubed. And we're looking for dv dt. We're given dx dt, I believe. No, we're actually looking for dx dt, how the side is increasing, but the volume, the rate of volume is given. So once in a while, you're given the rate of volume or area, and you have to work backwards. Okay? So you take the volume equation, v equals x cubed, and you differentiate. So you'll get dv over dt equals to 3x squared times dx dt. And we can plug everything in. So dv dt was 2 equals to 3 times 3 squared. So I believe you'll get 2 over 27. And that's dx dt. And that should be centimeters per minute, I believe. Yep. And that's how fast the side is increasing. And the last example that we're going to discuss actually is sliding ladders example. This tends to be a common one. This is, if you draw an example, it's an example of a right triangle, which we'll see again in chapter 7. So it's important to note. So let's say a 17-foot ladder is placed against the building. I kind of tried to draw. This is a ladder. The base of the ladder is slipping away, so it's moving in the positive. It's slipping away from the building. So notice how I drew this arrow here at a rate of 9 feet per minute. And find the rate at which the top of the ladder is sliding down the building at the instant when the bottom of the ladder is 8 feet from the base of the building. So it's a mouthful, but it's important to draw and label everything. So we're given that the base of the ladder is slipping away. We're actually given dx over dt. So be very careful when you label them so you don't get them confused, because they are different. So we're also given that the bottom of the ladder is 8 feet from the base of the building. We're actually given x equals 8. So typically one of the sides is not given, and we have to find it actually using Pythagorean theorem very shortly. So y is not given, and we're also supposed to find out how fast the ladder is sliding down. So dy over dt, typically that would be a negative rate because y is decreasing, but the answers, because it's a rate, is sometimes written as a positive on your, erase this, on your homework. Okay, so let's take a quick look. So it's the Pythagorean theorem is x squared plus y squared equals to 17 squared. So we solve for y, that's 15. Actually 8, 15, and 17 is one of the common Pythagorean triples. If you ever take standardized tests, it kind of helps to know a little bit. Then once we know that, you go back to the equation x squared plus y squared equals to 17 squared. Why I kept 17 squared is because the length of the ladder is a constant. So you actually keep it as a constant because it's never going to change. So notice the x will change, the y will change, but 17, the length of the ladder would never change. But there's another example later on where it does change. So be careful. With ladders it doesn't, but there may be other examples where it does. So you take the derivative, so we'll get 2x times dx dt plus 2y times dy dt, and again this is equal to 0. Then you can plug in, so it's 2 times 8 times 9 plus 2 times 15, and you can solve for dy dt, and I believe I got dy dt to be a negative 4.8 feet per minute, or 24 over 5. So the answer should be negative again, but I think if it's specified that the ladder is moving down, then you can say it's at a rate of a positive rate. So in the answers in my math hub, for example, that's how you would specify. Okay. Then we have a few other examples in that section. I think there is a similar one that I wanted to show you where there was like a rope, and this is where r was a constant, but there was the height of the dock, I believe there was a constant, where the length of the rope was a variable. I called it r, but it worked very, very similar. Notice how it's just, you keep it x squared plus y squared equals to r squared, but you can actually solve for r the same way, but the length of the dock, the y squared, would be constant, which is why I kept it at x squared plus a squared equals to r squared. So when you differentiate, so one of them usually would be a constant, even though it's not always the hypotenuse, but everything else is very, very similar. So this is it for this section.